In this series of videos, I'm attempting to repair and restore a PDP11-34A vintage computer. In the videos so far in this series, I've been through the system, and initially it did seem to boot up, and I was kind of glossing over a lot of the issues that I was finding with it. And I tend to do that in my videos. I like to stay focused on a particular aspect of the video. I'm trying to keep on topic. And it's very easy to get distracted and go off topic and start talking about things that are irrelevant. However, someone asked an extremely good question in response to one of the previous videos, which I just want to touch on the comment before we get into the real meat of this video, because it was a really good question, and I think it really goes a long way to explaining what we tend to find with this type of machine when dealing with them. And the question was, considering that the machine seemed to work when I first assembled it and put it together, why did it suddenly develop a lot of faults? And it kind of didn't. As I say, I was skipping over a lot of the repairs I was doing. I tend to do that when I'm posting these videos. I just want to show the machine and try and make sure people's interest is retained. It can get very long-winded, as you're finding with this series, when you start going into detail. But I already knew the machine had various other faults, and especially with the CPU system. And because of the nature of these machines, quite often faults that exist don't show up until you do some specific testing. And what can happen then is, if other faults develop along the way while you're still dealing with it, it can kind of paint you into a corner where the machine isn't really then running well enough to carry out tests to easily locate the faults. And you then have to kind of move over from the system level fault finding, where you have a logic analyzer connected to the Unibus, for example, to looking at the blocks of hardware to see what's going on and where the faults lie, and then try and resurrect it, get it running again, so you can then continue doing the more in-depth fault finding. So a very good question, but I don't think it developed a lot of faults suddenly. But having said that, one of the things you will find with machines like this, it's got well over 1,000 ICs in it in total, and it's been stood idle for decades, corrosion building up in the backplane, possibly issues with the power supplies. And when you bring them back to life and start using them, you will start to get a rash of failures. And it will appear as if the other machine's going to completely fail, but it will, in theory, or mostly, they settle down after a while and the failures become fairly few and far between. But you do need to be prepared. If you get a machine like this and plug it in, it will work, or may work, and then within a day or so it will just die, and you can then start chasing numerous faults around. At the end of the previous video in this series, I had an issue in that the CPU would not complete a microcode cycle. I'm not going to go into too much detail about what the microcode is. If you're familiar with it, then I'll just give a quick explanation as to what I found. But if you're not, then bear with me. I will be posting a completely separate series of videos on the inner workings of this CPU, and I will go into a lot of detail. But in short, the microcode generator or system is really the heart of the CPU. Now, if you've read my book on the transistor processor, the microcode system is equivalent to the control matrix. And what it's for is you feed in a binary value to its inputs, and in this case you can view it as a 48 data output ROM, and the individual outputs change in response to the input value you apply to it. And those outputs are used to control various aspects of the CPU, whether it's to enable a buffer or to cause a certain behavior within the ALU. It enables the system to manipulate all the sub-blocks to carry out certain tasks based on the instruction cycle it's currently trying to carry out. Now, part of the requirement for the CPU in this sort of architecture is that the microcode generator can actually make decisions, and it's not making decisions on the same level as the main CPU, but it is able to branch. And it does that by having on its input there are a series of buffers that buffer the input value, and then on the output the pins go to various control lines. But you can modify the input, matching an address, but you can modify the input address based on the current status of the CPU. So in other words, as the microcode is progressing through the instruction cycle, it might jump within the microcode sequence to a different area, different part of the code, depending on what the CPU is currently doing. Now that is where I found the problem. It was doing a jump, should have been doing a jump, but it was jumping to the wrong part of the microcode. And so where it should have been carrying out one particular function, it was actually trying to put data out onto the unibus, which it shouldn't have been doing. And that was causing the memory card to do weird things, and once it does this, all bets are off, of course. If the microcode generator isn't running properly, then it's not going to work. So that was just a faulty IC in the feedback loop of the microcode addressing. So I fixed that, and it will now go through a microcode sequence. It's not booting up yet. There are other faults. This comes back to why does it develop multiple faults. And bear in mind, I've been working on this now for several weeks, so it has had quite a few hours now since it was kind of brought out of mothballs. So it's well into the realm now of ICs failing because they haven't been used for so long, and now they're powered up and expected to do something useful. So the way I found the issue with the microcode sequencer is I had the logic analyzer attached. I loaded a specific instruction directly into the CPU, and then I applied this connector up here. You can apply two signals. One will disable the onboard main CPU clock, but then you can apply clock pulses, and it means you can single step through the microcode. This is not the single step that you get with the button, which single steps through the instructions. By applying single clock pulses, you can move the microcode sequencer on one microcode step at a time. And that's how I found that the output was expected to loop back and change the input address to a certain value, and it didn't. One of the bits was stuck, so it was jumping to the wrong part of the microcode. As I say, I will come back to that and explain it in more detail in a future video series, but I need this to be working before I start that series, because otherwise it will just be very confusing, because we'll be looking at faults rather than its proper operation. Now, once I'd done that, it was at the point where it would at least run all the way through some instructions, but it's still not running. And in this video, what I'm going to do is look at the testing I did next to find out exactly what the next step in fault finding should be. So there are many different ways you can do this. I'm not saying that what I'm doing here is the right way. And some advice I got while doing this from someone in the US was about a possible tool for fault finding. I'm looking to purchase one, so if and when I can get that, I will post a video on it, but for now I'm just using what I have here and what I've been demonstrating. So the next step was to try to see if the CPU could load instructions from RAM. It won't run if I try and load a test program. There's one particular test program I use a lot that's come out of one of the original documents, and it just puts a value, or zeros the value in the R0 register, puts that value out of the serial port, increments the value, and it just keeps looping round and round doing that. It's quite a useful test program because it tests quite a lot of the system. But what I was doing was using the first instruction from that to test the microcode generator, because I know what it's supposed to do, and I've used that quite a few times, so I'm familiar with what the CPU should be doing. That helped me track down the microcode fault. What we'll do now is start going through that test program and see how far through we can get, and that should in theory give us a good clue as to what the remaining or the next issue is that we need to address. Before I switch the PDP on, we'll have a quick look at the test program. The instruction I was manually loading into the CPU is this first one. It's 5000. This is octal numbering, of course. So 5000 octal, and that instruction just clears the R0 register. The next instruction loads a value of 177564 into R1. That address, we'll come back to the actual addressing later, but that address is to access the status register of the serial transmit register. And the next instruction, this is where the main loop of the program starts, 105711. That tests a byte value, and the actual value it's testing is the value that's pointed to by the address in the R1 register. In this case, it's testing the value of the status byte in the serial TX register. And the result of this, the N flag will be 1 if the value is less than 0, and the 0 flag will be 1 if the value is 0. It then goes on to check the flags, and it will carry on and continue if the serial TX register is available. If not, it will just wait, and it will keep looping around until the register is available. When the register is available, as indicated by the TX register, the TX status register, it moves on. So the next instruction will move the value in the R0 register. We zeroed that at the start, and it will move that value into the address pointed to by the value in the R1 register plus an offset of 2. That's what this number here is. And in other words, what this will do is it will move the value in the R0 register into the serial transmit data register, and it should then send it out to the remote terminal through the serial port. It then increments the value in the R0 register, and it then jumps back to address 1006 octal, which is the start of our main loop. It will just keep doing that, so it loops around here waiting for the serial transmit to complete. It then sends the next data byte, jumps back to the start, and then waits for that byte to be sent as well. What I'm going to do to start with is just load the first instruction and then the last instruction and see if it can loop round continually, zeroing the R0 register. So we'll get this booted up. Unfortunately, I will have to turn the fan on, otherwise the boards will overheat. So it will be a bit noisy, I'm afraid, but I'll start by just simply loading the value of 5000 octal. We'll use an address for our program of 1000, and then we'll try and run it and see what happens. I've got the fan going, so I'll boot up the PDP, and now we'll select address 1000, enter the instruction that we want to use, which is 5000, and then the next two instructions will just cause it to loop back to that first address. Okay, and before we start, we'll have a quick look at the address of the R0 register to see if there's a value in there to start with. So that is at address 777700. We'll have a look, and that's currently got a value of 400. So we'll go back to our start address for our program. We'll try and run it, and as you can see, it is running just round and round in the loop, so we can stop that. We'll examine the register to see if it actually zeroed it, and it did indeed zero it. So that tells us quite a lot already. We've made a huge step forward. The CPU can now load instructions from the RAM. The error light on the RAM is off, so you can't see it. It's kind of around the back of this main board, and it was coming on every time I tried to run a program before, and that was because of the behavior of the microcode unit putting data onto the bus when it shouldn't have done. But it's getting the instructions from the RAM, and it's the correct instruction. It's also then able to execute that instruction, so the microcode is completing, and also the addressing and calculations for the jump are working as well, so it's going back round, and we can kind of prove this by single stepping. You can see it just jumping between 1000 and 1002, which is what it should be doing. So what I'll do now is enter the rest of the program, and we'll see if this runs, and if not, where it makes an error. Okay, I've entered this program. If we enter the start address of 1000, we can examine this and we'll see that all the values are correct. So what we'll do now is try and run that. You can see if we run off the end, we've got the default value for the memory. Apologies if this display is flickering. Again, that's just an artifact of the shutter speed of my camera. So what we'll do now is set the start address of 1000 and we'll try and run this. And you can see it runs briefly and then stops. We can single step through this, and it is looping around, but it's obviously then stopping for some reason. It's not continuing to run. What we can do is have a look to see if it is incrementing the R0 register, and it does appear to be incrementing the R0 register, so we'll step through a few more times. And we can see that that is actually incrementing, so it is going round, and at this point it is incrementing the register. So I've already got suspicions now as to what this might be doing. So what I'm going to do now is try manually writing to the TX register. In fact, what we'll do first is we'll check to see if the transmit status register is showing us the correct value. So if we enter the address for that status register, it is indeed showing 0. And what I'm going to do now, I won't show you the terminal screen. I have got the terminal hooked up, but I'm going to try sending data out of the TX, the serial port. So I need to enter the data, the address of the TX buffer, and that's 777566. I'm going to send a value of 101, deposit that. Although you can't see it, I can confirm that the terminal is showing an uppercase A, and that's what the value 101 represents. So we know that the serial port is working, but one of the things you may have noticed is that when I typed in the address through the console for the serial port, I used the addresses 777564 and 777566. But in the program listing, I've used 177564. That's not an error. That's just because you can't store a value of 777564 in 16 bits. We've only got a 16-bit word for the instruction, of course. So the way that the CPU maps data, or maps the addresses, is it effectively remaps addresses, so the upper bits are effectively always 1. So if we were to send this value out of the CPU, what should be put onto the Unibus is 777564 and not 177564. So what I'm going to do is switch on the logic analyzer, and we'll run the program. We'll try and trigger off the 777564 address and see if it's actually putting out the correct data value onto the Unibus. So looking at the logic analyzer, I've got the address set as 777566, and if the decoding is working correctly on the CPU, we should hit this address when we run this program. So we'll arm the analyzer. I'm going to try and run the program from address 1000. And it's gone through, it's failed to run. I'm going to single step it a few times, and as you can see, we're not capturing anything. What I'll do now is change the trigger and see if it's going to allow us to capture the address, the base address that we're putting in, rather than the remapped address. Try running again. Still nothing. So clearly it appears we have an issue with the mapping of the CPU, and it's not correctly addressing the peripheral cards. This is a sanity check. What I'm going to do is try to manually write to the address that we've got set. So I'll set the address back to 777566. That's the correct address for the card, although we're accessing it through an address of 177564 and 177566. It should still trigger when we try to access it with the address we've got set here, because of the way the CPU should remap the addresses. Okay, so I'm going to enter the expected address 777566. I'm going to try and send a value, and as we can see, it has successfully triggered. So the console is correctly sending data to that address, but the CPU is not correctly mapping the instructions to the Unibus. So we're making progress. We now know that when the CPU tries to access the peripheral card at address 777564, it's not correctly remapping the value that we've got in the instruction here. So it looks like we have an issue with the remapping of the addresses on the CPU. So it could be as simple as a bus driver is not working correctly, but now I know at least we've got the microcode unit working. I can start looking into why we are not correctly accessing the serial card. I don't think it's a serial card issue, because the address shown by the logic analyzer is correct when we use the console. It's just when the CPU is trying to use an instruction, decode it, and then access the Unibus that it's incorrect. So I think it's an issue with the CPU addressing and remapping. So that's what we'll look at in the next video.